memory and what are some tools that can be used to assess the memory of your PWA or Chrome feature that may impact one. So when we started out with this problem of looking at PWA memory, we had one representative PWA. So when we started out looking at this, we had one representative PWA we were looking at, and we thought, okay, well, let's get a baseline. Let's understand how good we can be if we optimize absolutely everything. And to do that, we made what's basically a blank page progressive web app that's just a blank page and a manifest, and took memory measurements of that. And we ended up going with just the most top level number that Android surfaces, which is proportional set size or PSS, and measured that. And we got some pretty startling results, which was that the blank PWA used 85 megabytes and our real PWA used about 80. And no, just a blank. It's a blank page, no JavaScript. We separately looked at one with a service worker as well, but this one was just completely blank. So anyway, this result, clearly something seemed up. We were like, why is the blank page using more memory than the real one? And so we decided to see how we could understand this memory and maybe get some clues. So the first thing we looked at was, is PSS the right thing to measure? And PSS is kind of a measurement that tries to take into account shared memory and private memory. So if Chrome has multiple processes, this measurement was from both the browser and renderer process summed together. And if two processes share a 10 megabyte blob of shared memory, you don't want to count it twice. So PSS gives you a way to sort of divide through and account for that. And although there are some issues with PSS, that really isn't, measuring PSS wasn't what was causing this weirdness. So we moved on and said, what's another way we can split this? And what we arrived at was, let's look at dirty memory and clean memory. And dirty memory is sort of memory the app has written to. It can't be recreated trivially. It's your typical Malak memory, things you create with new, things that, if you allocate shared memory and write to it, these are all going to generate dirty memory. Clean memory, on the other hand, is memory that the OS can sort of throw away and bring back with no intervention on the app's part. That's something like a the code pages, the actual code that's being executed for Chrome. If we throw that out and we need it later, the OS can just read it back off disk. There might be a performance hit, but there's nothing about it that there's no intervention needed on the app's behalf to handle this. So we ended up looking at that, and we re-sliced these two measurements by dirty and clean memory, and things began to be a little bit clearer. The first thing was looking at dirty memory. We could see that, okay, we're now seeing the pattern we expect, where if we just look at dirty memory, the representative PWA was using more memory than the blank page PWA. Looking at clean memory, we see the opposite pattern, which is what was causing this weird discrepancy. And after a bit more investigation, we found that the issue is really clean memory is hard to measure, and a lot of this clean memory isn't actually needed anymore. So as you loaded the real PWA and started applying memory pressure to the system, the OS would start discarding parts of this clean memory. And if it was never needed again, it would be gone. It would never come back. And so what we're seeing here is kind of an artifact of that. And so, well, this raised the question, can we just ignore the clean memory? Can we just go ahead and say, let's just focus on dirty? And while that's mostly true, I do want to call out that there's sort of this concept loosely of having like busy versus idle clean memory, where idle clean memory is memory that maybe it's a code page that's used at Chrome initialization. It's never going to be used again. And if we discard it, there won't even be a performance penalty. There's no penalty. You can just throw it away. Whereas busy memory, you might have a code page that's used in Chrome's rasterization. And if you have an animation in your PWA, you're going to need that every frame. And so this memory, if you throw it out, will be reloaded almost immediately at a big penalty because disk reads are slow. And so that memory really isn't free. It's not something we can just toss out. Unfortunately, there isn't at least on Android, there isn't a really great way to get this breakdown. And it's not really a clean breakdown either. It's more of a spectrum of how busy is the memory. So we did decide to go ahead and just mainly focus on dirty memory for the rest of our analysis. But this is just something to keep in mind, given that clean memory did account for so much of that baseline PSS size. So going back to this, if we just look at dirty memory, which we said, all right, that's fine, but we still have 25 megabytes of dirty memory for basically displaying nothing. Why is this the case? Luckily, Chrome does give us good tools to understand why this is the case. And we were able to break this down. I'll go into which tools those were a little later in the presentation. But in general, this is broken into a few chunks. The biggest chunks being OpenGL-related memory, Java Android-related memory, Chrome Malak, and V8. Yep. Yes, all the numbers here for simplicity are summing across the browser and the renderer. So just to run through these quickly and kind of explain where they came from. GL memory, this one, it seems like we're doing very little, but at the end of the day, you have some textures. This was sort of expected, as even a blank page, we need one texture for the screen. And potentially, if there's anything on the page, and I think in this case, I actually did have a hello world text on there, so it wasn't completely blank, you end up with a tile or two. And so you do have a few textures. The screen on this device is 768 kilobytes, so it kind of makes sense. 1.2 megs, this seems reasonable. The other chunk was buffers for commands, objects, and shaders in the GL driver. This also is sort of reasonable. We found that this was an unfortunate thing where this is pretty much pre-allocated and stays at a fixed size no matter how much content we throw at it. So this is a case where the driver's kind of just going out ahead and pre-allocating buffers that aren't really needed now but will be needed later. So this was not too interesting. Neither was the next section, which is Java memory. We looked through this. Again, you might say, well, we're not doing anything, but Chrome actually does a lot, even with a blank page. It sets up Android views. It sets up OpenGL. It handles input. It logs metrics, among other things. One area we did find for reduction here was that PWAs actually have no omnibox. And so there are some omnibox related structures getting set up. So that's actually an interesting area to look at in the future in terms of reductions. Finally, V8 memory. V8 memory, it was also interesting because the page has no JavaScript, but it does appear that every page, no matter how simple, gets a V8 isolate. And a V8 isolate ends up with using about 1.5 meg, even with nothing going on. And that was a little surprising to us. And so we kind of dug into this and found that there's a lot of code space, which is typically used for compiled JavaScript. In this case, it was the built-in system, like the built-in functions and system libraries for JavaScript are pretty much pre-compiled and pre-instantiated in each V8 isolate. And so there is actually ongoing work to load these on demand, which would drastically reduce the blank page size, which isn't really meaningful because people don't browse blank pages, but will reduce the real page size as well. And finally, the last category that really made up a big chunk was Malak memory. And Malak memory, the big cases here were sort of caches. This included things like the user profile, history, services, and some support structures for OpenGL shader compilation. Again, these are all things which are kind of preemptively being done by the blank page and will be used later. We actually were able to find, as part of this investigation, some opportunities for memory reduction here. And this graph is taken after these went in. So we noticed there were certain caches that were using more space than they should, and we were able to tweak them down. So kind of to summarize, why was the blank PWA 85 megabytes? Well, mostly it was clean memory. And that clean memory is not that, as we said, it's hard to know exactly how much of that is needed. And that's mainly code pages and sort of libraries. A small chunk is dirty memory for the blank page, and we have kind of this detailed breakdown there. But a lot of that was caches and things that are pre-populated in order to make rendering go smoothly once we actually start showing real content. And so we were kind of satisfied with this for the most part, because you're going to eventually show content. If you load Chrome and just go to a blank page, it's not incredibly useful. So I will hand things off to Chris.
Great. So how about a real PWA? We also looked at a representative PWA. It's actually a Google internal application, but it does some graphics things and has some state and has a non-trivial amount of JavaScript, including the usual things like templating libraries similar to React. So if you look at the increase over baseline, there are a number of categories of increase. This is like a pie chart breakdown of them. The ones that are pretty large that you can already see for yourself is the V8 heap for allocating objects in JavaScript. Is a pretty big increase. CC means things allocated by the compositor. And basically this means more tiles to be shown on screen. And I'll get into that more in just a minute. And then there was Malak and partition alloc, which is as you create more DOM and you create more other objects in Blink, then you're going to end up with more allocations there. So let's go into V8 memory as a first category. So the increase, as you might expect, or expect or not expect, is almost entirely the heap. It's not the code. So similarly to what Eric was saying earlier, all of the built-ins were already accounted for. So the delta is just additional memory for whatever code the application is actually using. And then the heap for the variables that it allocates. So for example, in this particular PWA, we found, well, I'll go into that in just a second. And of course, like this all depends on what kind of site it is. So it's not really something that's global across all PWAs. So to diagnose this heap memory and find out whether or not, we wanted to find out first whether or not there's something that Chrome is actually screwing up on, but also like to see, as a kind of like as a test case, can we find a large piece of memory that's allocated by this particular PWA that could be removed with work by the developer themselves. So we used the V8 memory tab from which you can take a heap snapshot. And then we found that there was actually one or two very large strings in the application which represented a serialization of the DOM and all of the CSS. And the reason they had that is because there was a templating library in use, which would basically operate on a string and generate DOM text from the template when you change properties of the template. And so it, by default, the thing has all of the content of the web page in it, which includes a copy of your CSS. So that, and then in this case, the CSS was quite large, and so you'd end up with a huge string. So the point is, like, there can be some overhead, and it's mostly up to the developer in this case. Now moving on to the compositor memory, we see that a small fraction of the memory is decoded images, but most of it is actually tile memory. So first focusing on the small one before I get to tiles. Decoded images, you load like a PNG or something off the network, and then you need to decode it. And often the decoded size is much larger than the encoded. That's the whole point of encoding compression. But also the decoded size can be much larger even than just decompressing the gzip or whatever algorithm it is, because you can actually have images be at scales that are other than the intrinsic size of the image. So actually, the mismatch between those was one of the things we identified as a potential area of improvement. And it turns out that decoding things actually to the scale that you're going to display them on the screen, as opposed to the intrinsic scale and then doing a post scale in the GPU, is actually kind of a known thing that we've been wanting to do for a very long time. And it actually turns out that now is an opportune time to do it, because there's been all this work, some of which I referenced this morning, about doing independent processing of images to the rest of the display list when you're doing rastering to the screen. And so because we've sort of already done this work to separate out images as a concept, there's actually not that much more work to basically figure out the correct size you want to decode it to in order to display it, and then modify the decoders to choose a different MIP level or something to display it. So that work is actually underway this quarter. And then there's tile memory. And tile memory is basically proportional to the size of all of the composited layers you have in your app. I know, and I'm going to go into quite a bit more detail about that now. So, you know, a typical mobile page has, you know, has the base layer, which is always there, and then maybe it is scrolling if the app is written well, or there might be a different scroller for some reason. And then you often have like a couple of things that sit on top of it, like a fixed banner at the top and a sliding menu on the left. And because those things move differently than each other, they end up in different composited layers. Furthermore, on Android, all devices are considered so-called high DPI, which means that all of the divs which have overflow scrolling on them, including, well, the root always is a composited layer, but any additional div which has overflow scrolling on it will get its own composited layer. So if the scrolling thing happened to be a different div, it would get a duplicated extra composited layer. So here's a diagram of it. Okay, so let me get into some of the reasons for layerization, which will give you some flavor of maybe why there's so much tile memory being taken up, and how like it's actually kind of difficult in many cases for developers to reason about it. Just as like a quick piece of information before I go into details, we actually have a metric tracking the typical number of composite layers. It doesn't tell you the size of them, but it tells you the number of composite layers on mobile sites, and it's something like 40 or 50, which is kind of like surprisingly high. And we think, though we're still doing experiments, that a lot of the reason for this has to do with the difficulty for the developer to reason about all of the ways in which composited layers are triggered by content in your document. So like I said before, on a high DPI screen, if elements scroll differently than their parent, then they get a composited layer backing. And the reason for this is so that you can scroll them really fast with low latency. You don't have to raster anything super fast. But it does have a cost. You know, like Eric said, every full screen composited layer is 768K on a very low end Android device, and more on a high end device. And if it's composited scrolling and therefore probably exceeds the height of the screen, you're going to get up to 4,000 pixels on every other side, and so you're going to get a much larger amount of potential memory. Though we do have things which avoid computing more than one tile off the screen. A second reason for layerization is if you have any sort of transform or opacity animation, and this is regardless of whether or not there's any 3D involved. So if you just put a 2D transform on an element, it will not get a composite layer. But if you throw an animation to make that transform, you know, like if you want to shift it back and forth with the CSS animation, all of a sudden it'll be composited always. And there's actually nothing you can do about it as a developer to prevent that if you wanted to save memory. So this is actually one of the things we're looking at right now. We're running experiments to determine whether or not we can turn off compositing for perhaps all 2D and regular opacity animations, and then see if that impacts frame rate, if it impacts memory significantly. And third category is elements which have a 3D transform. And basically for correctness reasons, we must have 3D transforms allocate a composited layer. There are all sorts of reasons for that. All the way through the stack, there's basically data structures kind of assume that they don't know anything about 3D. And then moving on to the ones that, so each of these three things, like you could explain to a developer and they could get it in 5 minutes. It's not a big deal. But there are all these indirect reasons for compositing. For example, if you overlap with another composited layer and you paint after it, then you have to get your own composited layer to avoid drawing incorrectly to the screen, because things that are painted later, of course, draw on top because they stack on top. So those are forced to be composited. If you have a CSS animation on something, then actually Chrome is not currently clever enough to figure out where that animation might go to, and it assumes it might go anywhere. So if that animation, in principle, could have like transformed the element over on top of you, if the transform was cleverly done, then your element will be promoted to a composited layer. And so this particular thing leads to a whole lot of extra composited layers. Because for example, like suppose you have a mobile website that has just like a spinner on it, like a little spinner, and like, oh, I'll do my spinner with a 2D transform and a CSS infinite animation. That sounds great. You might end up with a lot more composited layers. And you also need more composited layers if you have a clip or an effect or a transform that contains other composited layers. So if you have like an overflow clip with children that are composited, then you're actually going to need another composited layer to represent that parent, because that's the way the compositor works. And actually in the representative PWA we looked at, there was a problem there because input elements are implemented in Blink as a scrollable layer, sort of like a regular scroller, because input can overflow, and the overflow has scroll bars and it kind of behaves like a scrollable layer. And so until a few weeks ago or a month ago or something, we treated it like any old composite layer, and it's like, oh, you're a high DPI screen, I want to accelerate and make your scrolls fast, so I'm going to composite you as an input box. But that doesn't really make any sense, because all of the input events come to the main thread, so you don't really want composited scrolling, and you're not really going to be typing that much text into your boxes anyway, especially on Android. So we went ahead and turned off. So and as a result, in this particular app, there was like kind of there was these input boxes that were in a modal dialog that kind of shifted around in an animation, and the animation used a 2D transform. And so because the input boxes were composited, the thing with the 2D transform ended up composited, and you ended up using a whole megabyte of extra memory to represent that thing. So if you just turn off the compositing for the input elements, you're helping out the developers a bit by not making them think about this particular use case. And there are even more ones that have to do with weird corner cases of the current compositing architecture that are difficult to get correct without overly promoting things. Okay, so I'll speed up a little bit. I think I guess we have a little bit more time. Okay, so you can identify layerization with the Layers tab in DevTools. It's an optional DevTools feature you have to access with the 3 dots menu on the right. And it can tell you sort of like a visualization of your layers a little bit. And it also tells you the amount of memory. You can see the third line there, it says memory estimate something. And it also tells you the best approximation to the reason that we composited. So things like clip with composited descendant will be listed there, and it'll say, this is why you were composited, because you had a clip with composited descendant, or assumed overlap due to a 2D transform animation somewhere on the page. And so developers can take action on this by trying to rework the way that they structure their DOM to avoid such situations. And here's an example of, let's see, what happened here. Oh, so this is just an example of layer explosion. Each of these red boxes is another composite layer. Okay, so we're working on the things I already told you about, like kind of short-term things about turning off certain triggers and adjusting things and tweaks and so on. Longer term, Living Paint V2 aims to be a much more flexible system for avoiding compositing when you don't need it, and understanding better what's going on so that you can avoid things. We'll also be able to like better budget how much memory you have. So on low-end devices, we can be much more aggressive about not promoting things. Yeah, and so on. So by working on this particular PWA, we were able to reduce by several megabytes, because they had that modal dialog with the full screen transform thing I told you about. They also had several other things that you could tweak to reduce the number of composited layers. And in fact, we found that on very low-end devices, there's an interesting trade-off there where memory is so tight that if you allocate, say, 5 more megs of memory, so on these are 512 megabyte devices, and unfortunately, Android itself uses 350 or more of those megabytes for itself. And then maybe there's also like the launcher thing, which is running. So you should only plan on having at most 100 megabytes for any application. And so like an extra 5 megs could cause your app to run out of memory. Or if you want to like be able to switch between 2 apps without having them constantly reload, it could mean the difference between those things. And so actually avoiding every single compositing trigger and making it just a single 768 kilobyte texture can be a big deal. So also the JavaScript source has to be, Blink keeps a pointer to the JavaScript source at all times, even after load of the page. And the reason is because V8 does incremental compilation of the script. And when it needs to execute more script, it'll actually go back to the source and do it. And there are very good performance reasons to be doing this. We discussed with the V8 team. This is a topic which has been discussed many times, and it's a difficult issue. So you end up with a whole bunch of extra memory due to a reference to the actual JavaScript source. So takeaways: you should keep an eye on your JavaScript usage. The smaller the script, the smaller that pointer to the source is going to be. You want to reduce your composite layer count as much as possible, subject to performance memory trade-offs. Like sometimes composite layers can help performance quite a bit for scrolling and so on, but you should be cognizant of the trade-off. Use dev tools and be aware that layers beget more layers. Layer explosion is a thing. So I'll pass it back to Eric.
So really quick, just to kind of finish up, I wanted to discuss kind of the tools we use to collect a lot of these numbers because they're pretty useful if you haven't seen them. And the main tool we were using was memory infra tracing, which was added by, I think, a number of people have worked on that, including a lot of people from the London office. And basically, anytime you're taking a trace in Chrome's normal tracing dialog, you can go in and check the memory infra box, and then you end up getting a full memory dump every, I think, 30 seconds. And these memory dumps just show up in your trace as a little dot you can click. And if you click that, you get this great breakdown of basically where all Chrome's memory is going by process and by subcategory. This is a cool thing where if you're working on a new feature, you may consider instrumenting it to work well with the system, because then you get your own category here, you can report your memory, and things like our perf lab will potentially catch regressions in the numbers if your memory usage increases down the line. We don't have a ton of time to go into details here, but this is just a great tool. This is what we used for the majority of our numbers, and I've added some links at the end of the deck, which I'll share out, that show you how to get more information on this tool. So yeah, so basically to summarize, using the techniques we've discussed in this talk, we were able to get this PWA's memory usage down by over 5 megabytes on certain screens, which is a big deal when you're dealing with the 100 megabyte limit, basically, and your app starts at 70 megs. Or 80 megs. And these changes included both things in Chrome, which are rolling out from 60 to 62, as well as a number of changes to the PWA itself. So it kind of has to happen on both sides. And yeah, so a lot of these changes should actually benefit everyone. They weren't necessarily specific to the PWA we were looking at. So that's the end of our talk. And like I said, we'll share out this deck, and I guess we are almost out of time here, or we're out of time. So if there are any questions, I guess we can try to answer them quickly. Okay, so thank you.